TF Pytorch Jack's neural networks assignment that I was working on. So to begin, I'm going to talk about the Numpy neural network since it's the simplest of the libraries used to make neural networks. And the data I decided to use is a data set that I used in a previous assignment about environmental safeguard metrics used to calculate the cost of companies that use different environmental resources, and the target is the estimated environmental impact as a percent of the revenue in that year for that company. So it will be bigger if the revenue made by the company outweighs or does not outweigh the environmental cost. So if the environmental cost or the environmental impact is bigger than the revenue, then it'll be a more negative value, meaning that the effect on the environment is larger than the revenue the company is making on those resources. So I did some pre-processing, and I'll only have to go through this step and for the different notebooks, as it's the same data for all the notebooks. One of them has synthetic data generated from this data, modeling the distributions. So I decided to scale the data since it'll hopefully help the model perform better. And then I plotted the data distribution without scaling and with standard scaling to show how it affects the values. So we see X is the first biodiversity variable, the Z is the working capacity 3, and the Y is the biodiversity 1. So these two are similar. Z is working capacity. With standard scaling, it's easier to compare since they all are in a value relatively close to each other, 0 to 3, instead of in the thousands. And then this also affects the color variable, which is the target prediction environmental impact. So darker values have more impact on the environment. You see there's like two planes, one here and one here, and then it's connected by a line. This is the model. As MSC uses linear layers, and it's non-linear model, so it uses ReLU. And this is how the model is constructed. Then this is a test of training the model, and now here the model is being trained on 3 variables, and these are the scaled as well. So this biodiversity 0, biodiversity 1, and working capacity 3. Earlier I talked about how I chose these since in the box plot we saw that biodiversity 1 and 2, they have a tighter range, and in the description of the variables it says that biodiversity is the environmental impact from mining, of land use and toxicity, not mining. So land use I felt was very generalizable metric since many companies own land. It's one of the most I believe to be one of the most impacts on the environment, and so I thought choosing these two would make the model more generalizable. And after evaluating the results and plotting them, we saw that in the trials for different epochs and different number of hidden layers, neurons, we see that it varies every time you run it, since it varies due to how the model is trained. But here, the lowest loss is given with a input of 100 and output of 50 for the neurons in the 2 layers. And then the final output layer is the prediction, so that's 3 layers. The 3-layer model with an extra 2 nonlinear layers. So the first time I ran it, it was 3264 was the best neurons to train the model, but over here we saw it's 150. And also for the number of epochs, when I trained it the first time, I think it was 20 trials, and here I think 40 is the better number of epochs. So yeah, it varies every time you run it, and that can be changed. So here I set the model to calculate the predictions with the scaled data, and this is the truth value and this is the predictions. We see since that we used only 3 of the variables, predictions are kind of not looking the same as the truth value. However, yet we were able to make a model using Numpy. And then in the JAX neural network, it is essentially a more advanced version of the Numpy model, and it can be used on CPU, TPU, or GPU, given the JAX Numpy library. And so the preprocessing is mostly the same, and the data this time was expanded to not just use the 3 variables, but all the data, which is more like 18 variables, including fish production, crop production, meat production, more variables on working capacity, biodiversity, abiotic resources, etc. And I left out the year since I'm not doing a time series analysis, I'm just doing a regression. And can skip the processing step, I already went over that. And the Numpy JAX model difference is you replace more of the Numpy methods with the JAX Numpy library methods, and had to modify one of the random generation methods from Numpy to use the random normal distribution for generation of the weights at the start. And the rest of the model architecture is mostly the same. So it has more features this time, and this time it's also using the JAX library for Numpy. So it can run faster, it can use more variables and features. And here 256, 128 neuron size with 50 trial epochs worked better. And this is the truth plot of the truth value distribution. This time it's flipped, so we don't see the other plane on the opposite side. And these are the predictions made by the model. So it looks closer to the reality. It is a little bit more darker, meaning that it's predicting more negative values in this model than in the truth. But it's still less negative values than in the other Numpy model, meaning the predictions did get better. And now I'm going to move on to the Pytorch notebooks. Pytorch model was also trained on the entire dataset, and this is using the low-level Pytorch API. So it's possible to create your own layers and train the model using your own methods. And the loss here is lower than in the Numpy and JAX models. So I think maybe the Pytorch methods did help a little in improving the accuracy. And in the high-level notebook using the high-level API, we also see the same accuracy. Maybe it's a little bit more improved. The definition of the model is also, it looks cleaner. It's a more simple. It's using the API, the more advanced API, so many of the methods are already created in the Torch library, and they just needed to be put together. For example, instead of Numpy nantanum, we have Torch nantanum. So it's a wrapper around Numpy, and so it does many of the same methods. But I didn't have to define the classes, it kind of already handled it. And so the model, it was more simple definition using the sequential layer. And so the average MSE is 0.06, average RMSE here is 0.26. In the low-level API, it was 0.004 and 0.06. So it looks like the low-level API might have gotten a little better accuracy with root mean squared error, but similar in mean squared error. And this is the even more advanced API Lightning API of Pytorch. And over here you can see that it is implementing the Lightning module. It's still using the sequential layer, but now the training and the validation and the test and optimizer and other parameters are defined in the class as well. So you can create the model and then train it using one line after defining the model, using the fit method, and then inputting the train loader to load the batch data. And then after training with 20 epochs, the test loss is 1.10, and this is using the MSE, the mean squared error. So it's higher than the lower level or medium level Torch API. So I think having more flexibility is good, and maybe using the lower level APIs might be a better option if you want to fine-tune the model and increase the accuracy a little more. Now I'm going to talk about the Tensorflow API. And in these two notebooks, I tested the low and high level Tensorflow API, and specifically in the low level, I tested a forward method using matrix multiply. And in the high level, I tested the built-in TensorFlow einsum method. So in the low level API version, and also in the TensorFlow section, I created synthetic data. So instead of training on the actual data set using all the variables, I created synthetic data for the three variables used in the JAX and Numpy section. I'll talk a little bit about how that was processed. So feature selection, I just selected the three variables that I selected in the Numpy and JAX notebook, as I thought that they were going to be a little bit more meaningful than the rest, but that's subjective. And then I looked at the distributions and saw that biodiversity had like an exponential, the target had like an inverse exponential, and biodiversity and working capacity had a very mixed looking distribution that I thought maybe it was a Gaussian, but after looking at it, it might be an exponential with a outlier in the center. So I used this function to create the distributions for Gaussian exponential and inverse exponential, and then I added a shift to the exponential based on the graph that I saw above. Since it was negative, and see the target, this is the real data distribution, and then this is the synthetic distribution. So for the target, the mean was -1, here it's -1.9, here's -1.14, working capacity 3, the mean is 443, here it's 442, so it looks close. However, the overall distribution is much more full than in the actual data, and it's not as more regular in the synthetic than in the actual. And I used 10,000 samples, and then the rest is the same. I added it to the data loader in Tensorflow, and then I created the Tensorflow model, and here's the Tensorflow matrix multiply method. And it was very important to use float 32 types for this method. I think these are double. This is also known as a double. And this is a simple model. However, it still does gradient descent and can be trained. So here I trained it using this train on batch method. And after 30 epochs, the loss was 0.21. And I output some predictions. Since I didn't include a test method, I wanted to just visualize what it looked like. The loss on this prediction was 1.0, so higher than in the training. And then this is what the real truth data looks like. This is not the synthetic data. And then this is the real labels. Or sorry, the real data with the predictions made by the model trained on the synthetic data. You can see it doesn't look very similar. This is the simulated data distribution and target labels. So we see this is the simulated data, this is the real data. The shape is different, and the values are also different. However, I can see what it's trying to do here. It's trying to match the environmental cost intensity, that the color it's not completely even over here, and over here it's completely scattered. And then this is the simulated data predictions, which is like a gradient, and it seems like it's lighter on this side, darker on this side, meaning the intensity is meant to be a little bit more negative, with higher biodiversity value or working capacity value. I don't know if that holds for the actual simulated data or for the real data. So yeah, the low-level model, that's what the predictions look like, and then for the high-level model, it's also using the same simulated data, so I won't go over that again. And then this is what the model construction looks like. It's using an Einstein layer, using the Tensorflow layers late.layer class, and then it is adding a kernel to multiply the input with a equation that is defined here, which essentially performs matrix multiplication. The Einstein layer is a little bit more optimized, so this might improve the performance. And then it is a 3-layer model with the Einstein layer, and it's also using ReLU, so it's nonlinear. And it's using the mean squared error as the accuracy as the metric to evaluate the performance. And it's being trained here. It gets final accuracy after I think there's no specific number of epochs defined. It's just training on the data set and doing it in batches. After that, the loss or the accuracy is 1.0, and then in the test, accuracy is 1.1013. And then I made predictions on the entire data set, the synthetic data set, and then using the test data set. Oh no, on the whole real data set is the X, and then on the synthetic data set is the test predictions, which is the X test. And then I made a plot, a 4D plot, but I only selected the 3 variables that I thought were interesting to visualize it. So it is trained on the whole data set, but I'm only plotting the results on 3 of the variables for simplicity of the plot. And this is the real data set. This is the predictions made on the real data set. And then this is the simulated data set. And this is this prediction made on the simulated data set. And we can see that it looks more true to the distribution of the synthetic data, the predictions, than it does on the real data. However, it looks better using the Einstein method than when using the low-level API. So that was all for this assignment. I think I got to explore this data set very well now, and I think that each library has its own use cases, and they're all very interesting